Hello, this video will be about the Nobel Prize in Physics from 1915, awarded to William H. Bragg and William L. Bragg for their services in the analysis of the crystal structure by means of X-rays, an important step in the development of X-ray crystallography. This will deal with the lectures given. First lecture given by William L. Bragg, the diffraction of X-ray by crystals. I made a summary of it and I'm going to read it to you. In his Nobel Prize lecture, Bragg showed how he was led to make the discovery. Nature had given with crystals a diffraction rating suited for this purpose. It was also known that if X-rays were electromagnetic waves, the wavelength should be very short, about 10 to the power minus 9 centimeters. Zonka, Fedorov and others showed that the atoms in a crystal must be arranged with perfect regularity and that the spacing must be about 10 to the power minus 8 centimeter. This relation between the spacing and the wavelength was required for diffraction. Verlauer with Friedrich and Knipping passed a narrow X-ray beam through a crystal and found immediately evidence of regular diffraction. Was also a Nobel Prize awarded for that. Much more investigations have followed since. Von Lauer first worked with a crystal of zinc sulfide. He showed that the structure of this crystal was cubic. He developed a mathematical theory of diffraction by a space lattice, and the diffraction pattern was caused by atoms in a cubic space lattice. The diffraction of X-rays was discovered by von Lauer. X-rays, of course, were discovered earlier by Röntgen, also Nobel Prize, first Nobel Prize for Physics, 1901. The theory predicted that there were a lot of directions in which the diffracted rays can go, but only a few of these were found. He suggested that only certain wavelengths were present in the beam, and that the found diffracted beams belong to those present wavelengths. I thought the answer may lie in the crystal itself. What would happen if a series of irregular pulses fell from a regular space lattice, on the space lattice? I considered, this is Bragg of course, the consideration of the diffraction effects as a reflection of the pulses by the planes of the crystal structure. The point of the space lattice may be arranged in a series of planes, parallel and equidistant from each other. As a pulse over each diffraction point, it scatters a wave, and if a number of points are arranged on a plane, the diffracted wavelet will combine to form a reflective wavefront, according to the well-known Huygens construction. The pulse reflected by successive planes build up a wave train, which analysis shows to be composed of the wavelengths given by the formula n lambda is 2d sinus v, with n is an integer, lambda is the wavelength, d is the spacing, and v is the glancing angle of reflection. This is also discussed in the earlier video on the general information. So I'm going to skip that for now. It still left open the question why some planes reflect and others equally suited do not. The answer was that the diffraction centers were arranged in a face-centered cubic lattice and not on a simple cubic lattice. The former is a cube with a point at each corner and at the center of each face. Zinc blende has such a simple cube lattice structure, and it explains von Lauer results. Potassium chloride has a simple cube lattice structure, only points at the corners, and thus another diffraction pattern. This fitted von Lauer results, see figure 1, you'll see that later. There still was the possibility that the diffraction was not the result of X-rays. My father did the experiment. He sent X-rays to a crystal at all possible angles. Very strong reflection happened at some angles, and it followed the above formula. The first evidence of the existence of the characteristic lines, a power method of finding the arrangement of a form, is a crystal. The instrument used was as the predecessor of the X-ray spectroscope. The crystal structure of calcite, zinc blende, fluorspar, and iron pyrites were analyzed. It was possible to calculate the spacing between the reflecting planes and assign a wavelength to the characteristic lines in the spectrum. Results agreed with the K or L radiation first discovered by Bragg, also Nobel Prize. The spectrometer gave us the frequency of these radiations. My father showed that the frequency F times Planck's constant H equals the energy E required to excite the rays. The quantum law was proved for X-ray. This von Lau's discovery had led to two branches of research, X-ray spectra and crystal structure. Moseley was the first to take a survey of the X-ray spectra, and he found a law which governs the number and the order of the elements. The square root of V is Z, with V is the frequency and Z is the atomic number. He found that in passing from one element to another in the periodic table, there was a regular progression of the frequency in the K and L radiations given out by the elements, and that its frequency was so great that it was possible to assign with an absolute certainty each element to its proper place in the list, and to fill the gaps where an element was not known. Moseley's early death in 1915 cut short his brilliant career at the outset. Since then, no one has done more for X-ray spectroscopy than Ziegbahn, also a Nobel Prize. There's a great accuracy and delicacy in his X-ray spectra measurements. He found the origin of the K, L, and M radiations after work by Kossel. Also, he found that there is a critical value for the absorbing power of an element. It gives direct evidence for the amount of energy change when an electron passes from one stationary state to another inside an atom. Dr. Lind used these absorption edges to study the chemical composition of the substances and the potential energy of the valency bonds. The examination of crystal structures with X-rays gave us for the first time an insight into the arrangement of atoms in solid bodies. A normal light microscope cannot. We cannot see details smaller than the wavelength of light with it. By using X-rays, the limit has decreased 10,000 times, so now we can look inside a molecule or an atom. The limits of the crystal patterns are arranged on a space lattice. The measures of a unit cell of a crystal must first be found. This comes down to finding the D in the formula. We already seen the formula, and lambda is 2D sinus phi. Then we can calculate how many atoms there are in a unit cell. Next step is to determine how the atoms are grouped together to form a unit. This is done in a similar way as a spectra obtained by diffraction grating. I skipped the details there. If you want to read it, you have to go to the original text. The link will be in the description. The structure of the groups of atoms influences the strength of the various reflections. The rays are diffracted by electrons grouped around the center of each atom. In some direction, interference strengthens the beam, and in other, interference cancels out the beam. The arrangement of the atoms can be found by comparing the strength of the reflections from different phases and in different orders. Earlier we made assumption to the reflection coming from the crystal. We assumed that the diffraction only takes place at the center of each atom and that the effect of an atom was proportional to its atomic weight. Even more important, that it is shown that even very slight variations in the relative position of the atom greatly influences the strength of the beam. The made assumptions are therefore still used. We started with analyzing a number of crystals. A single crystal is employed in the X-ray spectrometer. The crystal is placed so that the zone is parallel to the axis, and then it is turned around, and the reflections of various phases are measured. This is an improvement over a goniometer, which can only measure the angles between the phases. An X-ray spectrometer can also measure the spacing of the planes, even the crystal may have no regular external form. Bhadeshia and Scherer and also Ho overcame the difficulties with not perfect crystals. A monochrome beam of X-rays is allowed to fall on a mass of crystalline powder. Some of the crystals will so as to reflect the rays for every phase in order. The resulting diffracting halos are recorded on a photographic plate. Many elements were so analyzed and can also be used for non-crystal substances as long as the substances, crystalline or not, are not too complex. But the whole method is a new approach and has great potential. Development of this power method is study of colloidal particles, tiny particles dispensed in a fluid. This is done by Scherer. It seems all solids can be analyzed with X-rays. One type of chemical bonding has already been confirmed, that is including chloride, see figure 1. These atoms are not associated in molecules but are ions which are held together by electrical attraction. This is in line with the work of Kossel, Borne and Landré. Knowing the chemical composition can also help to determine the crystal structure, as my father did with aromatic organic compounds, such as those with benzene rings. Probably other complex crystals can be analyzed in this way also. A still deeper explanation of X-rays is the structure of the atom itself. The wavelength of X-ray is shorter than the atomic diameter, and one may expect electrons to diffract X-rays, making it able to get some idea of their distribution in the atom, since interference will also place. Douwe and de Bijen-Compton are all working on this. There have also to be made many unproven assumptions, and there are many experimental difficulties, but there is good hope a usable method will be found. And it was. Well, here you can see the link to the complete lecture if you want to read that. This is a summary. This will also be in the description of the video. And here you see the figures that are in the PDF of the lecture. Only it points the lecture only points to figure 1, as you have probably noticed. Well, if you want to study in more detail, you better go to the Nobel Prize site or pause the video. That's also possible, of course. Then the other Bragg, the father, William H. Bragg, he did not give a Nobel Prize lecture. So instead, something about crystals, coming from the free book by Harshad K. Bhadeshia. Hope I pronounced it correct. Geometry of crystals, polycrystals and phase transformations, and made a summary of the first chapter. And here it comes. Chapter 1, Introduction and Point Groups, non 1-1 Introduction. A crystalline state is characterized by regular arrangements of atoms of large distances. These properties vary with direction. This is called anisotropic. Crystals can be 2 or 3-dimensional. See figure H11. We will see that shortly. Whether or not 1 and 4-dimensional crystal exist is a matter of debate. Crystals are often beautifully faceted, see figure 1-2, can be solid or liquid, and can also have arbitrary shapes. The beauty of the forms is caused by an attempt to minimize the surface energy per unit volume. For isotropic materials, the sphere would be the equilibrium shape, but crystals are anisotropic. The planes with the least energy tend to maximize the area. Engineering materials often use many crystals of various sizes and shapes, called polycrystals. Connection to crystals give a bicrystal with 5 degrees of freedom, 2 for the connected plane and 3 for the relative orientation of the crystal. Such crystals' properties depend on those of the crystals involved, but also of the compound. Then paragraph 1-2, the lattice. Imagine a 2D pattern of point. One sees the same pattern from any of those points. The pattern is thus periodic. Basic unit is repeated in both directions to repeat the whole pattern. This can be done in 3 dimensions with a unit cell, a 3-dimensional lattice. That unit is parallelepiped with vectors in 3 directions. See figure 1-4. See that later. Each cell has 8 corners. Each corner point is connected to 7 other unit cells. A cell has 1 lattice point at the corner, but can also have lattice points at other places. There are several possibilities for such an arrangement. I skipped it here. If you want to read it, go to the original text. The 3 basis vectors define the unit cells. The magnitudes are called lattice parameters. All other vectors possible in the unit cell can be written as combination of the base vectors. Example 1-1, primitive representation of cubic 4. See also figure 1-4. This has 4 lattice points. The primitive cell is trigonal and all angles have 60 degrees. Here you see the figures that are mentioned. If you want to study them, you better pause the video or go to the book via this link. This will also be in the description of the video. Then paragraph 1-3, Bragg lattices. The number in which points can be arranged regularly in 3 dimensions, so the stacking of the units is not limited. Bragg in 1848 showed there are just 40 lattices and 7 crystal systems: cubic, tetragonal, orthorhombic, trigonal, hexagonal, monoclinic, and triclinic. See table 1-1 and figure 1-5. You saw them here they are. 2-dimensional crystals and surfaces. There are only 5 possibilities for the unit cell. See figure 1-7. These can be derived from the projections shown in figure 1-6. Graphene is an example. Single layer of atoms, hexagonal 2D lattice. More examples are in the book, but I have skipped them. The surfaces of 3D crystals are known to be one of the 5 lattices discussed above. This is of course also important in processes that rely on a surface structure such as catalysis. Then paragraph 4, directions. A vector u can be represented as a linear combination of base vectors a1, a2, and a3. Thus, U is then U1A times A1 plus U2 times A2 plus U3 times A3, 1 for every dimension, of course. See figure 8. Sometimes the properties along two or more different directions are identical. The directions are equivalent. The crystal possesses symmetry. For instance, 1, 0, 0 is equivalent to 0, 1, 0 and 0, 0, 1. Also to minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. Here are the number of equivalent directions, or multiply here is 6. Example 2, given the number, I've skipped it, but you can read it in the book. Paragraph 1.5. If a plane intersects the A1, A3, A3 at distances x1, x2, x3, relative to origin, the Miller index of that plane is given by h1 is VA1 divided by x1, and the same is true for the other two, as you can see, in which V is a scalar. If the Miller index is 0, the plane is parallel to the axis involved. See figure 1.8. Then paragraph 6, Wies's own law. This law states that if a direction u1, u2, u3 lies in a plane h1, h3, h2, h3, then u1 times h1 plus u2 times h2 plus u3 times h3 is 0. This applies with any crystal system. Proof is in chapter 5. See also figure 1.9. Then paragraph 7, symmetry. Crystals can possess symmetry. In a cube, no edge can be distinguished from any other. An orthorhombic parallelepiped has a lower symmetry. See figure 1.10. Symmetry operations form a spatial arrangement in another that is indistinguishable from the original. Example, a 90-degree turn of cubic along the edge of a unit cell. Then you get the same as what you had. Deformations like this are known as lattice invariant deformations. The Bragg factor of these lattice factors. When the Bragg factors are not lattice factors, partial dislocation occurs. Then paragraph 8, symmetry operations. An object possesses an n-fold rotational symmetry if it coincides with itself upon rotation about the axis at an angle of 360 divided by n, with n as an integer. Possible angles are 270, is it probably 180, 90, 120, again 90 is it's superfluous, and 60. For n is 1, 2, 3, 4, and 6. Yeah, this must be 360, of course. Yeah. All of the 14 Bragg lattices have a center of symmetry. See figure 1.11. Rotation in the other way makes no difference. A rotation can be combined with a translation parallel to the axis to generate the screw axis of symmetry. The magnitude of the translation is a fraction of the lattice repeat distance along the axis. The operations of the glide plane combines a reflection, a mirror image, with a translation parallel to the plane, again through a distance that is a fraction of the lattice repeat distance. This translation may be parallel to a unit cell edge, in which the glide is axial. A diagonal glide is a translation along a face or body diagonal of the unit cell. The translation is a half or a quarter of the diagonal length. Example 3.1 gives a 5-fold rotation, and see figure 1.11, which shows that a 5-fold rotation is forbidden. It cannot happen. It's not possible. Here you see again the figures. Advice, if you want to study them, go to the book or pause the video. Then paragraph 9, crystal structure. Lattices are regular arrays of imaginary points in space. A real crystal has atoms in these points. Consider the projection of the primitive cubic cell, for instance in figure 113a, and B to E shows a pair of atoms, in this case of copper, at 0, 0, 0, and zinc at half, half, half. The motif placed in each of the lattice points to build crystal structure of figure 113.f. In general, one can say lattice plus motif is crystal structure. Another example is a figure 114. It shows diamond. Each has a unit has add carbon atoms to per lattice point. Figure 15 shows nickel and aluminium ions. As example 4, the structure of graphene, which is seen in figure 116 and 117. Then point symmetry, paragraph 10. See figure 118. The symmetry operation on a molecule constitutes a collection of known as a point group. Always one point is unchanged by the operations. The point group of a crystal is also the symmetry common to all of its microscopic properties like energy jumps, vibrations, and spectra. Translations do not occur in a point group, but rotations, mirror planes of symmetry of gravity, and inversion axis are permitted. There are 32 point groups in 3 dimensions with the 7 crystal classes. See also table 1.2 and figures 119a for an object in the orthorhombic class and 419b for the tetrahedral class. Higher order of axis, this means that there is a secondary axis and there may be even a tertiary axis. More on notation issues is skipped by me, but if you want to read it, go to the original book. Then example, symmetry of chess pieces, and figure 120 discusses the group symmetry of 2 chess pieces. If a crystal exhibits well-developed faces, its point group symmetry can be derived from its external form. See figure 121 for 2 classes, the gypsum. 122 shows 2 examples which one can deduce the crystal class simply from its symmetry. And there's example 1.5, octahedral interstaces in iron. See figure 123. There's another example. Here you see those figures. Again, if you want to study them in detail, it will take some considerable time. You better get the text or pause the video. This is the book, as you can see. Well, this has been a summary of chapter 1. Here you have the titles of the other 12 chapters for in case you're interested. Stereographic projections, stereograms for Laws symmetry systems, space groups, the reciprocal Latin diffraction, deformation and texture, interfaces, orientation relationships, crystallography of martensitic transformations, oriental relations, homogeneous deformations, invariant plane trains, martensite interfaces, and there are some appendices. Well, if you want to read the book, you can follow this link. This will also be in the description of the video. Well, this was a replacement for the missing lecture of the older of the 2 Braggs. For now, thank you for watching and maybe until another time.